Welcome. Today's notes worksheet is entitled Probability Day 2. We'll be taking a look at a couple variations of probability problems today. We'll develop a couple ideas around some formulas and then obviously reinforce those formulas with a few examples. So why don't we go ahead and start it out there. I've got just a preliminary example at the top and just talking about multiple events occurring. And so the question that's posed is, are the events dependent or independent? Just a couple buzzwords that you'll see over the course of the lesson here. And I guess just a quick explanation, and then you could probably use your intuition to do A through D. But essentially the question would be, when we have a secondary event occurring, I'm just looking at part A right here, are the outcomes directly affected by the event occurring first? So one more time here, are the outcomes of the second event occurring directly impacted by the outcomes of the first event? And so if they are, then the second event is dependent on the first event. If not, then the second event is independent of the first event. All right, so let's go ahead and take a look here. The secondary event for part A is flipping the coin again after flipping it the first time. Are the outcomes of this event occurring, are they directly impacted by what happened here, or would they be staying the same as if this never happened? And I guess the argument can be made that this is independent of what happens first. So sorry for all the circling there, but hey, long story short, I would argue that this is independent. The second event is independent of the outcomes of the first event. All right, letter B. Selecting a card from a deck, replacing it and shuffling, and then selecting the second card. So think about selecting this, and are the outcomes or the likelihoods, the probabilities, are they affected at all by what happened here if we replaced the original card after we selected it and then shuffled? Has anything changed? No. And in this case, I guess again, I would say the argument is that those are independent events. This is not affected by what happened here. All right, good. Letter C, selecting a card from a deck, then selecting another card. All right, so in this case, a little different now. That first card is selected and then put to the side, and then we select a second card. So now have the outcomes been changed from this in this second event? And I guess you would have to say yes. Obviously, if that first card has been taken out, there are no longer the same number of cards as when we started. And so obviously the number of outcomes have changed. And so as a result, the second event is directly dependent on that first event occurring. And then last but not least, rolling a die and then rolling that die again. Is this impacted by that first event? No. The likelihoods, the outcomes stay the exact same as if this never happened. And so as a result, that second event is independent of the first event. All right. Not a huge big deal there, but I kind of like talking about how one event affects another event. Will that change the probabilities of the second event? Well, if it's dependent, yes. If it's independent, no. All right, let's move on here. Looks like I've got a quick definition, a couple ideas to take care of, and then let's roll. So it says definition. When we compute the probability of event F, assuming that event E has already occurred, this is what is called the conditional probability. So the conditional probability of one thing occurring given that something has already happened. And we denote this probability by this right here. So we would read this as the probability of F given that E has occurred. Keep that notation in the back of your mind if you get an opportunity, as we'll be seeing that in action. And so as you can see on your paper, there's a general rule for computing the probability of one event given that the second event has occurred. And as you can see here today, it's going to deal with the idea of an intersection. So we're going to take the probability of the intersection of the two events occurring over the probability of the first event occurring. And as it says, guys, we're going to use this specifically on the back side, but we're going to focus on another piece to this puzzle in just a little bit here with a couple examples. So what we're going to do here is use that formula, long story short hopefully, we're going to use that conditional probability formula to find the probability, and here it is, guys, if you wouldn't mind underlining that, the intersection of two events. And so if you remember on the previous lesson, we talked about the union of two events. Now, guys, we're going to talk about the intersection of two events. And intersection would be something along these lines here. The probability of one event and a second event. Okay, so if you remember yesterday, and just really, really fast on this, the review or means add. If you remember that from yesterday, don't forget about, we talked about subtracting away the intersection, but typically in probability, or means add, whereas and that's what we're going to see today, means to multiply. We saw this with counting, and now we see it with probability. And here's the multiplication piece right here. So you can kind of see, guys, all I did in this particular formula is got rid of the denominator, pretty much brought that probability right up here, and that's why we have the probability of the first event times the probability of the second, given that the first has occurred. And that's how we're going to get the intersection. Okay. As you see this, obviously right now it's quite abstract in nature, but when we kind of see this in action, we'll get a little more concrete with it. So let's go try it out. A couple decent ones. I mean, nothing special about examples 2 or 3 here, but it definitely serves the purpose of putting that together. So let's see what we have. Suppose we draw 2 cards without replacement from a standard deck. What is the probability that both cards are kings? My apologies for not giving you a ton of room here. See what you can do with it. But basically, here's how I would argue it. What we're looking for is if the probability that both are kings, so we're finding that the probability that the first card is the king and that the second card is a king. Now, it seems kind of silly to kind of write it out that way, but I think that's helpful. All right, so there it is. There's the buzzword for the day, and. And so and means multiply. One thing occurring and a second thing occurring. So I guess I'll write it out here just the first time. I think that's helpful. If you don't feel the need, then don't bother. But basically what we're going to do is find the probability of the first event. So the probability that we take a card off the top and it's a king. And then what we're going to do is multiply by the probability that the second card is a king. And then there's the conditional piece, guys. Given that the first card is a king. So in order for these 2 events to occur, obviously the first one has to be a king, and that means that the second one has to be a king given that the first one was. So now at least I hope it's starting to come together a little bit with that notion of independent and dependent. It's done a little more implicitly with this, but I still think it works nicely. So let's keep it nice and simple. We'll do a couple calculations, get a little decimal on that, and end the story. So what's the probability that the first card is a king? Well, guys, there are 4 kings in the deck, 52 cards total. Not too bad. If you want to reduce that to 1 out of 13, obviously that would be ideal, but 4 out of 52 is not a bad start. All right, now here's the cool thing about this, just in my opinion. In order for the second card to also be a king, well, the probability now has been changed because we assume this is true. In order for both things to be true, we have to assume that the first thing occurred. And so now, what's the probability that that second card is a king, given that the first card was? Well, if you notice, it did say without replacement here, and so as a result, the 1 card's put to the side, so there are only 51 cards now in the deck. And again, what we have to assume is that the first card was a king, and so now there are only 3 kings left. Okay. And so basically this would be how we compute it. By the way, this would be 1 over 17 at this stage, and so I think we can kind of reduce that if you want. But I'll go ahead and just multiply those together, and I think we'll end up getting our nice little decimal on this. All right, so I hope everyone agrees. Just and means multiply. And now if you notice, the probabilities of the second event have been directly impacted by what happened here first. This is dependent of that. All right, so sorry for being too redundant on that piece, but anyway, hope it worked. Here we go, guys. So top, I think, was 4 times 3. Looks great. And then the bottom here, just a 52 times 51. And again, there are probably better ways to go ahead and express this. So it looks like we get about 0.0045 just from a decimal standpoint. Remember, our probability will be anywhere between 0 and 1. Obviously, in this case, quite a low probability, about 0.45%, give or take somewhere in there. Okay, good. And by the way, just sort of dawned on me, I just want to do this quick calculation myself. I think I reduced one of those to 1 over 13, one of those to 1 over 17. So theoretically, if I did 1 over 13 times 1 over 17, and you don't have to do this on your paper, just kind of thinking out loud there, I think I saw the chances would be 1 out of 221. I don't know. Good way to express that. I kind of like that fraction as opposed to this decimal, but whatever. Makes no difference. Cool. Let's do example 3. Suppose we draw 4 cards without replacement from a standard deck. What is the probability of drawing 4 of a kind? All right. I can envision probably 2 or 3 ways to do this problem, but I guess I'll take the approach that I've alluded to over the last 5 minutes or so, and that is kind of taking one probability and then the second and then the third and then the fourth and multiplying them together. So let's kind of start this out. For it to be 4 of a kind, I guess let's take a look at that first event occurring. In this case, guys, there are 52 cards in the deck. If we want to get 4 of a kind, how many favorable outcomes are there? And does it matter which 4 of a kind we get? No. So starting out, picking that first card, can't it be any card? Isn't that the case where really it's irrelevant? The first card is just going to set the precedent for the next 3 cards. Because now, here we go, we've got the first card and it's put to the side. And again, it was totally irrelevant as to which card it was. So in terms of the probability, it's a 100%. Favorable outcomes over possible outcomes. But now, everybody, there are only 51 cards in the deck. And what we want is the probability of getting the second card to be identical to the first card. Well, again, the idea is that we want the probability of the second event occurring given that the first one has. And so in this case, whatever card we picked, there are only 3 of them left in the deck. And then hopefully, just hopefully, you can see that pattern emerge from here. Because now 2 cards are set aside. What's the probability that the third card is the same as the first 2? 50 cards in the deck, and there are only 2 of that card remaining. And last but not least, 49 cards in the deck when I pick that 4th card, because we're going to draw 4 cards. And in this case, it looks like there's only 1 left. So what's the probability that that 4th card is the same as the previous 3? And so that's how it's going to play out there, just multiplication. And again, it's all and. First card and the second and the third and the fourth have to be the same. Hey, I'll just go ahead and grab my calculator. You guys do the same. Just at top, multiply them all together. Bottom, multiply it all together. Obviously, you can probably simplify this even a little better than I did up here. But I'll do it as a 52 over 52. Obviously, guys, that's just 1, but whatever. So I'll be kind of formal with it. There's your top. And then I had a 52 times 51 times the 50, and then times 49 down on the bottom, something like that. Again, so many different ways to express. And we obviously get quite the low number on this end. So I got 0.00048, something like that. All right. Obviously quite the low probability. Nice. All right, so just real quick there. Again, there are variations on this, of course, but generally speaking, or means add, and means multiply. And that's what we've come up with. Okay. You'll probably get some practice on those types. We'll go over just a couple other different types on examples 4, 5, and I believe there's a 6 as well. So here we go. How about you underline this piece for me? Just using a tree diagram, essentially, to compute probabilities. And it's just a good way to track multiple events occurring, and that's exactly what we'll do here. So let me read example 4, and let's go get them. A candidate for a driver's license is currently allowed to take a driving test 3 times before having to take or retake a preliminary written test. Some field candidates should be only given 2, yada, yada, yada. All right, that's irrelevant. Okay, here, guys, let's pick it up right here. So, from past history, 60% pass the driving test the first time, 75% pass it on their second try, and only 30% who take it the third time are able to pass. All right, very good. So 60% the first time. Those who fail get another chance. They study a little harder, so their probability of being successful goes a little, is increased a little bit. That's nice. Those who fail it 2 times get to take it a third. And quite frankly, if you failed the first 2 times, maybe you're just not meant for the road there. Well, regardless, only 30% pass on the third time. So from that scenario, let's see if we can break it down and do parts A and B. And it says, what is the probability that a candidate will fail the first time and then pass the test on the second try? So out of all the candidates that take these tests, if you were to pick one at random, what is the probability that this person would fit this category right here? Fail the first time and then pass the test on the second try. Well, in order to kind of work through this, it's good to see it visually. I'm going to try to build a little tree diagram down here, and I'd encourage you to do the same. But basically what happens, everyone, is you walk in the door, you take it the first time, and there are only 2 outcomes. And you can see my 2 branches of my tree. You either pass it or you fail it. Guys, throw a little P and F on those branches. So when you walk in that first time, pass or fail, history dictates that 60% pass it, 40% then fail it. Which means if you were to, again, select any person at random taking it the first time, there's a 60% chance that that person would pass, 40% that fails. Beautiful. All right, now, those who pass, you're done. End of branch. This ends right here. If you fail, if you go here, you're one of the 40%. The good news is you get to take it a second time. Same deal, of course, everybody. You walk in the second time, there are only 2 options, and you either pass it or you fail it. Again, throw another 2 branches, give me a little P and F on that. Now again, you studied a little more. In this case, if you're one of these people, 75% pass rate. Throw a 0.75 on that, everybody. That looks great, which means 25% still fail. Not cool, but still do. All right, again, if you pass, you're done, of course. End of story. One more scenario can occur here. If you fail 2 times, you get 1 more shot at it. So third time going through, you either pass or fail. Odds are a little lower, only 30% success rate, 70% fail rate. And so now we can talk about any scenario that occurs. Great little visualization. I kind of like that piece. So let me read letter A again, get back to that. What is the probability that a candidate will fail the first time and then pass the second test? All right, so let's track them. Walk in, what's the probability that you fail the first time? Well, the given probability there is 0.4. And then you walk in again, what's the probability that you pass the second time given that you failed the first time? Again, this only occurs because this happened. There's that dependence. I love that. And so, of course, we get that 0.75 right here for the probability of passing given that you failed the first time. Of course, what I want to do is find out what is the probability that the candidate will fail and then pass. And means you multiply the 2 individual probabilities together. And that's looking pretty good. So 0.4 times 0.75. Oh, I think I could do this one in my head. How does 0.3 sound? Please verify that. Which would be a 30% chance. So out of all the candidates, the probability that you select somebody at random and fits this criteria right here is 30%. Cool. Now, obviously, the sky's the limit with these. Let's just quickly do letter B and move on to the next. What is the probability that a candidate will fail twice and pass the test on the third try? All right, so let's see it in action. In order for this to occur, what's the probability that he fails and then passes? Track it one more time. Fails and then passes. Well, what's the probability that the person fails the first time? 0.4. What's the probability that the person fails the second time? 0.25. And what's the probability that the person then passes the third time? 0.3. And so what's the probability of all three events occurring? This, and this, and this. Sorry for being redundant, of course, but and means multiply, and multiply those together. In this case, I might need just a calculator to get me going. I might be able to pull it off, but I don't want to put myself on the spot. So 0.4 times 0.25, and then times 0.3. And there you go. And you could kind of look at that diagram and the information and realize that it was going to be quite the low percentage, so only 3%. Obviously, again, not as many people pass or fit this criteria. All right, good. So example 4, using that tree diagram to be pretty visual with it. Let's maybe do one more example with this, and then really a great problem to wrap up this notes worksheet. Here we go on 5, everybody. Marcella is taking part in a lottery for a room in one of the new dormitories at her college. She's guaranteed a space, but she's going to have to draw a card randomly to determine exactly which room she'll have. Each card has the name of one dorm, X, Y, or Z. Let's just keep it simple. And also a 2-person room or an apartment, so either room or apartment. And we've got all the data on what's available. All right, so it's fairly contrived here, but I think it still works. So Marcella walks in, she gets this card, and the first thing she looks at on the card is which dorm she's going to be in. And from what I see in the information, read it with me everyone, is that there are 3 possibilities. So when she picks up that card, she will either be in dorm X, dorm Y, and dorm Z. Based on the availability, the probability of being in one of those 3 dorms is as follows. So let's see, 30% on dorm X. Everybody, 50% on dorm Y, and 20% in dorm Z. So that's the first thing, is to kind of visualize those 3 individual probabilities, only possibilities out there. Now, not going to be great, but basically what happens is after she looks at the dorm letter, it will say either she's going to be in a room or an apartment. So I'm going to just go ahead and do R and A. R and A, last but not least, R and A. And so let's check it out here. We've got some information on each of those availabilities. And so let's put them in place at the end of each branch. So I'm hoping now everyone kind of can see the visualization of this. So what is the probability that it's a room in X? Well, 50% are rooms, 50% are apartments. For Y, 40% are rooms, 60% apartments. And for Z, 30% rooms, I'm getting 70% apartments. So take a look at the information in the problem, make sure that syncs up for you, because now I think we can track any particular scenario, and that's exactly what we'll do. So let's do letter A. What is the probability that she will select an apartment in Y? So again, you can kind of look through the information here, of course, but it seems to me that what's the probability that she gets dorm Y and she gets an apartment? I'm going to write it like that. You don't have to if you don't want to, but basically it's probability of dorm Y and the apartment. And again, sorry for the redundancy, just and means multiply. So we would say the probability that she gets dorm Y times the probability that she gets an apartment given dorm Y. Pretty cool. All right, the information's there. I didn't give us a ton of room to work, so I might have to come just over in this area right here. Hope you don't mind. Maybe you can find some space. So let's just track it out here. What's the probability that she gets dorm Y? 0.5. And then also gets an apartment. Here we go, 0.6. So 0.5 times 0.6. So I hope the interpretation does work for you, and I hope the tree diagram works for you as well. I kind of like that as a way to go through this process, seeing multiple events occur. And 0.5 times 0.6 should be 0.3. All right, let's do letter B. What's the probability that Marcella will be assigned an apartment in any one of the 3 dorms? Oh, that's kind of cool. I think we'll have to interpret this one. So probability assign an apartment in one of the three. So that means that she's going to be in an apartment in X, or the probability, well, let's do it this way. Sorry about that. Just kind of thinking out loud for just a moment there. So I guess I would say we want to look at the apartment in X or the apartment in Y. Oh, let's fix that just one more time, make it perfect for you. Or the apartment in Z. How does that sound as an interpretation there of what the problem is asking? So let's put this now together. We want the probability that she gets X and the apartment, Y and the apartment, Z and the apartment, and to me, I tried to kind of highlight that piece right there. What does OR mean in probability? Add. And so I see this as the probability of this occurring plus the probability of this occurring plus the probability of this occurring. So take a look at that. Just make sure that explanation makes decent sense, and then please run those numbers before I do. So what's the probability that she gets in X? 0.3, and then the apartment, 0.5. So again, X and the apartment, 0.3 times 0.5. Now plus. So what's the probability that she gets into Y? 0.5. And the apartment? 0.6. And last but not least, or it could be in Z, probability that she gets Z on her card is 0.2, and the apartment, 0.7. And put those all together, 0.3 times 0.5 plus 0.5 times 0.6 plus 0.2 times 0.7. So an interesting problem. It kind of combines the two things we've been talking about, or and all together there. I get about 0.59 when all's said and done. So probability that she gets an apartment is 59%. Cool. So look that over, and please, if something's lacking there for whatever reason, let me know. But this is how I interpreted these, and I tried to kind of write it out as best as possible. But you can see they're very specific types of problems. Let's do one more. So this is a really, really fascinating problem, and there's actually some precedence behind this. So let's look at it in a little detail. Going back just that first formula that I gave you, what's called conditional probability. And so the formula basically is the probability that one event occurs given that a second event has occurred is equal to the probability of their intersection divided by the probability of the first event occurring. So this would be kind of the favorable outcomes over the possible outcomes. That's how this sort of plays out when you talk about what is called conditional probability. And so let's read this problem and go through and watch what happens mathematically. It is completely surprising and really, I think, completely powerful. Here we go. Example 6. Suppose public health officials estimate that the incidence of a particular virus in the general population is about 0.5%. Furthermore, a test for this virus is 95% accurate. This means that the test would correctly identify someone as having the virus 95% of the time. Also, though, would produce a false positive 5% of the time. So based on these values, what is the probability that someone has the virus, here it is guys, underline that piece, has the virus given that he or she tests positive? So one thing, conditional on this thing occurring already. Okay, think about what that means. So what's the probability that someone has the virus given that he or she tests positive? So we'll kind of walk ourselves through the scenario here, but getting a positive test, what is the probability that the person that gets a positive test actually has the virus based on these numbers up here? All right, think about that. Now let's go put it in action. I've got a couple things written on my paper that'll get us started, and then I would totally encourage you to reflect on this one after doing it. Look back on it and see if you can make some sense of it. So here we go. It's the probability that the person has the virus given a positive test. Everyone okay? I just kind of stole that directly from the problem. And so what that basically means is we want the probability of the intersection occurring. So that would mean having the virus and having a positive test. So all I'm doing, guys, is just following this right up here. So it's the intersection. So it's the probability of having the virus and a positive test over the probability of that first event occurring. And in this case, it's given that he or she tested positive. All right, so is everyone okay with that interpretation right there? So for this probability to occur, we want the probability that both occur over the probability that the first thing has occurred, getting a positive test. So now let's play it out. Let's see what we can do. Now we're going to go ahead and do a tree diagram. And so this is kind of the last one on here. And so here's the scenario that I'm seeing. And if you interpret it in a slightly different fashion, that's okay. But here's what I'm thinking. So a person walks into the health clinic, and very simply, that person either has the virus or does not have the virus. So in one situation, it's this person. In another situation, it's this person. Either the person has the virus or does not have the virus. According to the public health officials, only 0.5% have the virus. So in terms of a probability, the probability of a person having the virus is 0.005. Which means, of course, 99.5% do not. So the probability that someone is selected at random and does not have the virus is 0.995. So to me, you walk into the health clinic, this is what happens first. You either walk in with the virus or without. Now you take the test. So guys, let's take a look and see what happens. Different meanings for two different people. It's either going to be accurate or not accurate. That means, again, different things for these two different people. But that is basically what's happening here. You take the test, and either it is going to be accurate or not. So let's see if, in this case, it says the test for this virus is 95% accurate. This means it would correctly identify someone as having the virus 95% of the time. So someone who has the virus, if it's accurate, it's going to detect it 95% of the time. 5% of the time, it will not. Okay, everyone all right with that? Now also, if you look, it says it would produce a false positive about 5% of the time. So for this person right here, which you can see is a very large percentage of the population, basically it is a false positive 5% of the time. So that means it would be not accurate. So that would mean it would tell you you have the virus even though you don't, 5% of the time. This is the false positive right here. But it does mean that it would say that you are negative, you don't have the virus 95% of the time. Okay. Look at that diagram, everyone, and see if that makes sense before we do the final calculation and round this out. And watch the number that emerges. It is totally shocking. So here we go. What is the probability of having the virus and a positive test? Remember, and means multiply. So having the virus, there it is, 0.005. So I'm going to go numerically right here, 0.005 times and a positive test. So that means this and accurate, 95%. Having the virus and it detects it. So positive test there. All right, now divided by what's the probability of getting a positive test? Well, there are two ways to get a positive test based on two very distinct types of people. You can get a positive test by having the virus and it being accurate, right? So let's put that down. Have the virus and it's accurate. Sorry for the delay on that. Let me finish what I had here. So 0.005 times 0.95. Now here's the thing. There is another way to get a positive test. And that would mean that you do not have the virus and it's not accurate, that false positive there. And so as a result, we would add this probability along with it, 0.995, being in that category, and getting an inaccurate test, 0.05. So take a look at that. Two different ways to get a positive test. One more time, having the virus and it being accurate, or not having the virus and it being inaccurate. Now watch what happens. Do the calculation, everyone. Do it ahead of me. And think about that. Think about all the people that would go in and get this test thinking it's 95% accurate, and that's good. But think of all the people that get a positive test. What percentage of those people specifically actually have the virus? So let me go ahead and bring this on over here just so I can do the calculation freely. And here's what I have. So 0.005 times 0.95. There is your numerator. Let's put it in play. Now divided by, here's the denominator. That would be the probability of actually testing positive, which we said can happen two different ways. And then plus 0.995 times 0.05. So one more time, not to be too melodramatic about it, but remember what's going on here. The probability that a person actually has the virus, given that he or she has already tested positive. So a person gets that positive result in his or her hands, what's the probability that you actually have the virus? Look at that. And as a result, you can see it's only about 8.7%. That's what's absolutely amazing. So if you kind of look at this, think of the hysterics you would create actually having people being tested. All these people that get a positive test, only less than 9% of them would actually have the virus. So this, to me, is sort of a misleading concept. It's this that I think that is so incredibly powerful. So look at that. I mean, just kind of reflect on that piece. I think it's a fascinating problem. And again, there is some historical precedence behind this. I won't go into that now by any means. I'll let you just kind of look over the math. And please ask questions if you have it on this one, because it's a pretty cool problem. All right, well, I'm kind of overstaying my welcome. Again, 37 minutes, yikes. So why don't I wrap it up at this stage? Please let me know if you have questions. Thank you for listening, of course.